Hi, and welcome back to this physics video series. So as you can see from the title, we're going to be talking about tipping in this video. Now I feel like not a lot of physics professors out there like to talk about tipping at all, but I feel like it's very mandatory to talk about it because when you get a problem like this, there's some things that aren't really intuitively known, and I'm just going to talk about them real quick, to be honest. So let's just imagine you have this chair right here, and the chair is going to have a friction with the floor. It's not like completely smooth. And so basically, in the end, the chair has a height of h, and you're going to be pushing the chair from the very top with like a force F. And you're going to basically see when this chair eventually tips. So basically, in the end, we need to start doing the sum of the forces, just like almost every other problem that we've done. So if we do the sum of the forces, and we're going to just start off in the x direction. So basically, we need to write down all the forces that are in the x direction. And so we have F, and we have our friction force. So F is in the positive direction, so we just write F, and then we're going to write minus our friction force, since our friction force is opposing it. And since this is a static problem, and basically it's not tipping at this point, we're going to set that equal to 0. And regardless, even if it was tipping, this has to equal 0 because it's not translating. Tipping just means it's going to be rotating around that axis right there. And so anyways, if you continue with this, your force in the end is going to equal your friction force. So they have to be equal and opposite in the end. And so if we continue on, we've got to do the sum of the forces in the y direction. Again, that's just going to equal 0 because it's a static problem. And then we're going to have basically N1, the normal force at the back leg, and then plus N2, the normal force at the front leg, and then minus mg, the weight. And so we get N1 plus N2 equals mg. The normal force is equal to mass times gravity. The typical scenario. But, we still have to do the sum of the forces, like I always say. So now if we do the sum of the moments, like I said before, we're going to be doing the sum of the moments about this point, which makes sense because it's going to be tipping like this. The chair is going to go like that. And you're not going to be rotating around this point. You're not going to be rotating around this point. You're going to be rotating around this point in particular. And I'm actually just going to call that point O. And so what I want you to do every time is actually write a little subscript of what point you're doing it about. That way you can reference it later when you're doing the moment for F, N1, N2, and so on, And so now this is going to be equal to 0. Not only because it's a static problem, like it says up here, but because we want to analyze it before it's tipping, basically when it's on the verge of tipping. And so we set it equal to 0, and we're going to have to do the sum of the moments for all these. And so we need to figure out the moment of basically like the friction force to start out. So of course the friction force could be just over here also. So it would be like mu times by N1 or mu times by N2. But in reality, I'm just going to write one friction force just because they share the same line of action, so they're not causing like a different moment. And I'm just going to call this one N2 plus N1, But in the end, since this line of action is going through the point that we're going through, the distance is 0, and so we don't include the friction at all in this scenario. So let me get rid of that line of action. So really, this causes 0 moment. Same thing for N2. N2's line of action goes through the point also. So it's just going to have a moment of 0 because it's a distance of 0. And so now let's move on to the weight. So let's just say, if we extend this length is just L over 2. So of course, it's not completely even, and it's going to be a little bit more than L over 2, but, just hear me out on this right now. It doesn't really change much. And so if we bust out our circle, we can notice that in the end, it's going to be like this. And basically, by using the right hand rule, you know, since it's going to be turning in this direction, if you curl your hand, your thumb is going to point outward. And so that's going to be a positive direction. And so then you get mg times by L over 2 in the end. And so now if we move on to the normal for N1, then we're going to have this part. And this is essentially going to be moving it in this direction. And if you curl your hands in that direction, it's going to be negative, just because your thumb will point in to the page. And so then we're going to have minus N1, and then the distance to the line of action, because this is the line of action, is L, you know? So then that's just going to be times by L. So now if we move on to F, then, so F is a little bit bigger. Here, let me just draw the line of action first. So if we draw the line of action, it's going to be like this. And so now let's get our circle out. And so in the end, then the force is going to push it in this direction. And if you curl your hand, this is going to be in the negative direction, just because your thumb is going to point into the page. And so it's going to be minus then F times by H, you know, just because the height of the chair is going to be the distance to the line of action. So in order to really analyze this, we have to get F all by itself. So what we're going to do is we're just going to add F times by H to the other side. So then we get F times by H equals, and then we're left with this one, and there's L in both of them. So we can take it on L. So then we have L mg over 2 minus N1. Then F is then going to equal L over H mg over 2 minus N1. So before I continue, I just got to point out one thing. If you remember from my normal force video, you would know that N1 has to be greater than or equal to 0. It can't be negative. And that's just because there's no guide that's acting on the chair and the ground in order to keep the chair from flying up. There's no guide, and so N1 has to be positive. And that's just because it's just two surfaces touching each other. If there's no guide, then the normal force can't be negative. And with this information, we can further analyze F. But how I want you to analyze F is just by, imagine you're pushing on this chair right here, and you're going to basically barely push on it until it tips over. And if we're barely pushing on it, then F is basically 0. It's approximately 0. And if F is approximately 0, then N1 has to equal mg over 2, just because this inside has to equal 0 then. L can't be equal to 0. And so if N1 equals mg over 2 is how N1 starts off, it can only decrease in order for F to increase, you know, just because it's negative right here. And so as N decreases, then F is going to increase, but you can't have N1 to be negative. And so in order to max out F in this scenario, N1 has to be 0. And so F then, we'll say F max, is then going to equal, here, make that into an M, is going to equal L over H, and then mg over 2. So in the end, you're going to actually have two F maxes. You're going to have the F max for tipping, and then you're also going to have F max associated with the friction. And really, when you're going to get a max for F, it's going to be when it's at static friction. Because after static friction, it's going to be kinetic friction. And basically, instead of having a static problem now where the chair is staying right there, you're going to have translation in the end. And so this is going to be max. Of course, you can keep on pushing it more until it accelerates. but in the end it's going to be mu s for it to just be static. And really it's going to be mu s times by n1 plus n2. And so in the end, now that we know that n1 has to be 0 for f max to occur, then this is just going to be 0. And that's the whole reason why I drew this friction force just right here. Just because you could have another friction force right here, but if the normal force is just 0, then it's non-existent also. And so that's basically why I just jumped to the conclusions and just drew it right here. And either way, we know that n1 plus n2 is going to equal mg. So in the end, then we get mu s times by mg for our f max. And so in the end, when we set the f maxes equal to each other, we will get this. So it's going to be mu s times by mg. Then that's going to equal L over h mg over 2. And so the mg's are going to cancel out on both sides. And so in the end, then you get this sort of group of scenarios. If it's going to be tipping, then you're going to have mu s less than L over h times by 2. And if it's going to be sliding, then mu s has to be greater than L over h times by 2. And so in the end, you get these two scenarios. So basically, if you have f pushing it and mu s is less than L over h times by 2, then it's going to tip and it's going to move forward like this, you know? Basically follow like somewhat this path right here. But if it's going to be, if mu s is greater than L over h times by 2, then it's just going to be translating in this direction, you know? And so in the end, you either get rotation or you get translation. Or you get both, and that happens when you set them equal to each other. And so mu s is then actually equal to L over h times by 2. And so in the end, if you didn't pay attention to any of this video, in which I really hope you did, just because I've been putting a lot of time and effort in this video so far, but regardless, if you did not, I want you to take away one thing from this video. And that is, if your object is about to tip, like this chair right here, then your normal force is going to be concentrated at the very edge. And it's going to be at the edge where it's tipping from, you know, or tipping about, you know, basically point O. And if you look at the Leaning Tower of Pisa, I'd be pretty sure that the normal force is going to be about like right there. It's not going to be at the very end just because it hasn't, a slight breeze would probably knock it over, you know, but there would probably be structural forces pulling it down. But if it was at the very end, you know, it wouldn't be so stable and wouldn't be up so many years. But regardless, just know if it's about to tip, it's going to be at the very end, the normal force. And there's going to be no normal force over here, just because that normal force would cause it to counteract the weight or whatnot, you know. Basically the moment's going in this direction. So, but anyways, another thing that I would like you to remember is that with buildings, there's usually not any horizontal forces. And so if you're gonna figure out if a building's gonna tip or not, a good indicator is that if you extend this line of action like so, if the line of action of the weight goes through the base, then it's definitely not going to tip. And so that is the case for the Leaning Tower of Pisa. At least I'm pretty sure. I have not gotten the center of mass for it, but I'm pretty sure it would be within the base, just because it's been up so many years, you know. And so that's all I have for this video. Please continue telling your friends or whatnot, and I'll see you in the next video.